Thanks. Yeah, so as Alex said, my name is Jim. That's my Twitter handle. I work at Hootsuite in Vancouver on our platform team. And this team is responsible for our microservice architecture and a lot of the shared backend services that the rest of the application uses. If you're not familiar with Hootsuite, it's the most widely used platform for managing social media, and we service over 10 million people. We have a web-based dashboard product as well as some native Android and iOS apps, and you can send messages, schedule messages, get analytics, things like that on all your social media. So for the past few years, we've been working on transitioning from a huge PHP application to a set of small Scala microservices, helping us scale our application and our organization. So I've got 4 things I'm going to talk about today. First, I'm going to give a brief talk about migrating from a massive monolith to microservices and some of the sources of complexity and failure that can be introduced when you're going through the process. Then I want to talk about asynchronous messaging, sort of in specific publish, subscribe messaging, and how it can help reduce some of these problems. And I want to talk about Kafka and how it's a great foundation for a reliable messaging architecture. And finally, I'll talk about Reactive Streams and Akka Streams in specific and how they can be used to easily work with Kafka from your Scala code. I'm not going to talk in detail about how to set up Kafka or do an in-depth tutorial on Akka Streams. So I want to start off by showing some complexity and sources of errors that are often encountered when breaking a monolith up. So most applications start off as a big monolith. So what do I mean by that? So it's like a single code base that the entire development team works on. Sort of a single source of truth for data, usually a single database, and a single deploy process. One build pipeline, one queue of changes that everyone is committing and waiting to be deployed. This is great for a small team. There's not a lot of moving parts. It's easy to iterate. You can make atomic changes just by doing a find replace on the code base. And everything's just a local method call away, or just a call to a central database. But a lot of the benefits of the monolith sort of become drawbacks as the size of the development team grows and the application becomes larger and larger. The efficiency sort of drops off. You get this big, fast, and then slow, and then slower, slower, slower. So as the application gets larger and larger, the build times get longer and longer, your tests take longer and longer to run, and one developer can break the build and no one can do anything for the whole day. You also need more coordination between your development teams to ensure that the application is always in a production-ready state. Some teams might need to wait for another completely unrelated feature to be complete before they can actually make their changes. Feature flagging can help with this, but it can become unwieldy with like a million if-else statements in your code. Also, you might need to scale the entire application when one small, highly used feature is being used, and it can often use way more resources and cost a lot of money. And it can be hard or impossible to try out new technologies or new application frameworks because your code is just in this big blob. An obvious solution is to start pulling off code into small services, decreasing the size of the monolith over time, and allowing teams to work separately from each other, and communicating via well-known APIs, usually something like REST over HTTP. Eventually, you pull out enough services from the monolith that the monolith sort of no longer exists. It's just sort of a facade that just calls backend services and aggregates the data that the client needs. So a microservice, to me, is a service that it has an independent code base, is deployed independently of the other ones. Each service owns its own data. It can do one thing well, and it's owned by a single team that has the power to make changes to it whenever they need to. And then it communicates with the other services via APIs. Microservices come with a lot of benefits. Since they're small and encapsulate one thing, build times are shorter, test times are shorter, deploy times are shorter. Each service can be deployed and scaled independently of all the other services. So this can save a lot of money compared to a monolith where you have to scale the entire thing. Each service can use whatever technology is appropriate. For example, an analytics service will probably have way different data requirements than a user management service. It's easy to create new services because they're small. It can help spur innovation in your company. Also, each service has a clear owner who's responsible for all aspects of that service. Sort of with a monolith, there's sometimes not a clear owner of functionality, or one person gets overburdened with ownership of everything. So microservices aren't a silver bullet. So you now get a distributed system, and all the wonderful things that come with that, like Dave just talked about. There's latency. All the calls become remote, which adds latency to everything. Any service or network component can and probably will fail at any time. So the system has to be architected with failure in mind. Also, the failure of a downstream service can cause cascading failures all the way up to any service that calls it. So an example, if you have 4 services here that are in sort of the critical path of your application, if they each have 99.5% uptime, which is pretty good, combined together, they actually only have a 99.5 or 99.9. They combined have a uptime of 99.5%, which is not good. It's sort of the difference in a month of half an hour of downtime to 3.5 hours, which is a huge difference. You also need a lot more coordination. Since there's no longer a single source of truth, it becomes more necessary for coordination between services. For example, if you delete a user from your system, cascading actions probably need to take place to delete it from all the other services. But having the user management system need to know about all the other parts of the system is not really maintainable. You also need more coordination between development teams. Cross-cutting changes can't be made easily anymore. You need to be careful with your API design so that you make backwards compatible changes. Can basically slow down the speed of changes you can make. And if you're not careful, the overall system can end up tightly coupled together and start to look like spaghetti, and you sort of end up with a distributed monolith, which is not good at all. But luckily, a lot of these calls aren't actually necessary to complete a user's operation in the critical path. For example, deleting a user doesn't really need to delete all their data synchronously. Or if you send a message to a social network, you don't need to tell the analytics system or archive the message synchronously. So a good way to reduce that complexity and lower the chances of failure of the overall user request is by pulling out non-essential API calls from being synchronous and blocking to be asynchronous. You get fewer calls in that path, you get a more reliable system. So rather than having everything be done synchronous, a service can send messages to an asynchronous message bus, fire and forget a message into the bus, and any other number of services can consume this information at their own pace outside of the scope of the user request. So why would we want to do this? It completely decouples the producer from the consumer of the information. For example, the service that reads and processes tweets from the Twitter fire hose doesn't need to know about the analytics system or push notification system that consume the data. Also, the point-to-point messaging becomes pub-sub. You can have one producer with many consumers. There's also less coordination necessary. So aside from agreeing on the message format, there's little to no coordination that has to happen between a producer and the consumer. Once something is producing data, it's really easy to add another consumer, and it doesn't affect the producer at all. You can also help scale your organization, as there's less back and forth necessary between development teams. A team doesn't even need to know who's consuming the messages that they're producing. So what sort of requirements are necessary for a good messaging system? You need well-defined delivery semantics on both the producer and consumer side. So like with at least once messaging, you have to deal with duplicates. With at most once, you have to deal with lost messages. And exactly once is really hard to do. You want it to be high throughput. We want the messages to send really fast. And we don't want to block the callers that are sending the messages. We want it to be highly available. We don't want failure of a part of the system to stop it from working. We want durability. So we don't want the failure of part of the system to cause data loss. We want it to be scalable, so we want to easily be able to grow capacity as the system evolves over time. And finally, we want back pressure. And so this is the need to be able to handle slow consumers of information as well as fast producers. So there's a ton of different messaging systems out there. And so which one should we choose? By the title of my presentation, there's a lot of different systems, but I found Kafka is one of the best ones out there. So what is Kafka? So from its docs, Kafka is a distributed, partitioned, replicated commit log service, which is a lot of fancy words together. But if you think of a commit log, think of how a database works. It's append only, linear reads and writes, so it's really fast at sending the information. It provides pub-sub messaging functionality, so one-to-many messaging. It was started at LinkedIn, but now it's an open source project and has a company called Confluent that sort of manages it. At a high level, a Kafka cluster maintains feeds of messages called topics. The entities that send messages are called producers. The entities that read the messages are called consumers. Pretty simple. The topics are a logical grouping of one or more individual commit logs, which are called partitions. And each partition is an ordered, immutable sequence of messages. This means that if a topic has many partitions, there's not a total order of messages in it. It's only per partition. And messages are continually appended to the log. Each message has a numeric position or offset in the log. And the messages are persisted in the log for a configurable amount of time, whether or not they've been consumed by anything. So the typical retention periods can range from hours to weeks, depending on the volume of data. The Kafka default, I think, is 2 weeks. We use this default at Hootsuite for most of our topics, except a few situations where we have extremely high volume topics where we lower that a bit. Producers, as their name implies, send messages to topics. They're responsible for choosing which partition to send the messages to. And so there's several different strategies that you can use depending on the ordering requirements. You can round robin the messages over all the partitions, which will sort of put an even amount of messages onto all partitions. The producer can also sort of consistently hash the messages over all the partitions, ensuring that as long as the number of partitions isn't changed, a message that has a given key will always go to the same partition, sort of ensuring an order for that key. I think one of the earlier presentations was talking about this with with a partition key that was sending tasks to be scheduled that would get scheduled by the same worker. But this can sometimes cause an unbalance of messages if one message key is super busy. So you have a really popular user, say like Justin Bieber or something on your Twitter account. You don't want all your you could have all the messages for that going to one partition, which would sort of overload the system. So it's a trade-off of ordering versus sort of scalability. Consumers, as opposed to many other messaging systems, Kafka consumers pull data from the partitions. They don't get push data ever. And all they track is their current offset in each partition. So this makes consumers really cheap. They just have to store a single number. And consumers are tagged with a group ID, which groups all consumers with the same ID into sort of a logical consumer. And each partition is assigned to only one consumer in a consumer group. So if all consumers have the same group ID, you sort of get a queuing message model where the messages are sort of sent to each consumer. If all consumers have a different group ID, you get a pub sub where the messages all go to all the consumers. And you need to ensure that the number of partitions in a topic is big enough so that there are at least as many as there are consumers in a given consumer group. Otherwise, you get some consumers sitting around doing nothing until another consumer in the group stops. So for example, in this, consumer number 6 is just sitting there doing nothing because there's only 3 partitions in the topic and there's 4 consumers in that group. But if, say, consumer 3 died, consumer 6 would get assigned a partition. So it can be kind of good for high availability. At Hootsuite, we usually use a single consumer group per service so that we can scale up and down the service knowing that each message will be only processed once by that service. So now that we have a sort of high-level overview of Kafka, does it meet those requirements that I was talking about earlier? Yes. So Kafka is super fast. It can handle a crazy amount of messages, hundreds of megabytes per second of reads and writes from thousands of clients. It uses immutable log files that are only appended to, so it's like an O1 operation just constantly appending. It uses the send file system call, so it sends data directly from the operating system page cache to the network card, so it never actually hits the application. And it uses the same in-memory as on-disk data structures, so it's really efficient at doing that. At a high end, LinkedIn had a blog post last year where they said they send 800 billion messages per day at 13 million messages per second, and 175 terabytes of data per day, which is huge. We're not quite at that scale at Hootsuite. We send hundreds of gigabytes of data per day to our cluster and sort of thousands of messages per second. Kafka deals very well with failure of any of its components. So for the Kafka brokers themselves, all the messages are persisted on disk. So if a broker crashes, it can just come back up with no data loss and sync up with the data that it missed. The partitions of a topic are replicated across the cluster. The replica is configurable, but you should always have at least 2. And if a broker crashes or shuts down, one of the other nodes takes over as the leader of that partition, and the producers and consumers just sort of seamlessly switch to using the other node. For consumers, since they're just storing an offset in the log, if they fail, they can just start back up and stop where they left off. And if they're in a consumer group, the partitions that were assigned to the one that died will just get reassigned to the ones that are still alive. For producers, they can be configured to retry on failures, which lets you sort of implement at least once messaging semantics, so you can just send the messages over and over again. We've had brokers fail with almost zero effect on the producers and consumers. The producers and consumers just sort of switch over to sending a message or consuming a message when the leader of the topic fails. It's also good when we deploy new code, because we just rolling restart our consumers, and they just leave. The partitions get reassigned, they come back, they get assigned back to it, and there's no data loss. It's also scalable. It's really easy to scale. If you need more capacity, you just add more servers, and then you can reassign partitions with the command line tool to move the partitions to a different node. Effectively, more servers means just more disk space in your cluster. Also, since partitions for a topic can be stored on different servers, the size of a given topic can actually be bigger than any one node can hold. And additional partitions can be added at runtime. If you sort of misjudged how many partitions you need, you can add more and they'll just get assigned to the existing consumers. It does change the hashing if you're using the hashing for message keys, so it could change which partition to get sent to, so you need to be aware of that. Kafka also helps with back pressure. Since it's this massive data storage, it kind of allows an almost unlimited data sync for your messages. And the per topic retention period sort of acts as a service level agreement for consumers. A given consumer has to consume messages within that period of time to avoid losing anything. For example, a high volume topic of ephemeral data might have a really short retention period. This way it's almost impossible for a fast producer to outpace a slow consumer. And this allows you to do real-time as well as batch consumers. So you could have a consumer that's consuming messages as soon as they come in, or you could have an analytics consumer that runs once a day that just does massive batch jobs on all the data that was stored. I want to make a quick aside about message data formats for messages sent to Kafka. In order for different parts of your system to take full advantage, they need to know what's in the message payload, and they need to be able to react to changes in that payload over time without dying. So Kafka only deals with byte arrays with keys that are also byte arrays. So you need to choose a format that is easily understood by all the parts of your system. This is even more important if you're in a polyglot environment. You're not just using Scala, where messages produced in one language need to be consumed by another. So what are some options? We could use serialization, but it has tons of issues with it. It's ridiculously easy to make backwards incompatible changes. Minor language versions can change binary compatibility, and it's completely incompatible with other languages. We could use JSON. It's a decent option. Everything in the world can read and write JSON. And the format can be evolved in a backwards compatible way. But JSON's pretty big. It's text-based and kind of slow to parse if you're parsing a ton of it. At Hootsuite, we've decided to use protocol buffers. So they're a binary format. They serialize and deserialize really quickly. It uses an interface description language for defining the message format, which then lets you take that and compile it into code for a whole bunch of different languages, which is nice. It's really easy to make backwards compatible changes if you follow a few simple rules that are on the protobuf website. One caveat is that serialized protobufs are untyped. You don't know what they are until you try to deserialize them. So we also pass type information along with it, saying this is the type of the message, so that the consumer knows how to deserialize it. We have this sort of central mapping of like a UUID to the message type. So now I want to switch gears a bit. So I talked about some of the problems that can arise migrating from a monolith to microservices and how Kafka can help with that. I sort of want to talk at the micro level now, so actually interacting with Kafka. If you're not careful, code inside a single service can become complicated and prone to unbounded memory use if you deal with streams. So I want to talk about Reactive Streams, Akka Streams, and how they can be used to simply and safely interact with Kafka. So Reactive Streams is an initiative to produce a standard for asynchronous stream processing with non-blocking back pressure. So a lot of stream processing systems don't allow a consumer to push back on the producer saying, stop, you're overwhelming me, I need some time to keep up. Reactive Streams has an explicit mechanism for a consumer to push back on that producer. And a publisher will never send more data than has been requested. But the Reactive Streams API is super low level and is mainly meant for library authors to use for implementing developer-friendly APIs and do compatibility between the two. So this is effectively the entire Reactive Streams API. There are three things. There are subscribers that can subscribe to producers who will send them a subscription that they can use to request messages to be sent to them. The publisher will then call on next with items. It could do that indefinitely if the stream is infinite, but if it's not, it'll eventually call on complete. That'll say that I'm not going to send any more items. If an error occurs, it will send on error. And then the subscriber can use this subscription to request that the publisher send it more items. And so this is the source of the back pressure. It can also cancel the subscription to say I'm not going to subscribe anymore. This API is really simple, but using it on its own would be kind of painful. So luckily, instead of talking about that, I'm going to talk about using Akka Streams, which is interoperable with Reactive Streams, and it actually uses it internally, but it uses Akka actors to implement the stream processing and has a nice DSL on top of it. So Akka Streams is built on top of Akka actors and Reactive Streams that provides a way to process data using bounded buffer space. So this is different than typical actors, which often process using unbounded buffers or using bounded buffers but drop messages when it gets full, which is neither of those is optimal. Akka Streams doesn't allow buffers to grow indefinitely, and it also doesn't drop messages. Also, unlike plain actors, Akka Streams are strongly typed. You don't have to deal with this any to unit nonsense with the receive method. So Akka Streams has a few core concepts that are used to construct stream topologies. There's a source, which is a processing stage with exactly one output and no inputs that emits elements to downstream stages when they're ready. There's a sink, which is the opposite. It's a stage with exactly one input that accepts elements from upstream and may push back on the upstream with back pressure. Then there's a combination of the two called a flow, which has one input, one output, accepts elements from upstream, and it also may push back pressure up. And then finally, there's also junction stages, which provide fan-out and fan-in capabilities. So fan-out, think of something like broadcast or round robin, and for fan-in, think of merging or concatenating streams. Once a topology has no exposed inputs or outputs, it's called a runnable graph and can actually be run. So processing stages are immutable. They're just a description of what to do. They can be reused and composed together, just like functions. So anything that has a shape of a source is a source. Anything that has the shape of a sink is a sink. And anything that has the shape of a flow is a flow, no matter what it actually looks like inside. So they're immutable blueprints, so you actually have to materialize them when you actually want to run them. So this is sort of like turning on the tap in the real world and making everything flow. And so it'll start actors to run the processing stages. It may open files or sockets or connections to resources. And these resources are automatically managed, so when the stream stops, they're automatically closed. Resources are released. Each graph stage can optionally provide a value during materialization that you can use to interact with parts of your system that aren't actually using Akka Streams. For example, a source can materialize to an actor that when you send it messages, it'll emit them downstream in the stream. Or a promise that if you finish it, it'll emit one message into the stream and then complete the stream. Or, a Reactive Streams subscriber to do some interoperability with Reactive Streams. And then similarly, a sink, you can get an actor that will get sent messages from the stream, or a future where you can be given the result from the stream and have a future that you can use with the rest of your program, or a Reactive Streams producer for doing interoperability with Reactive Streams. Or they can both return no value. So Akka Streams is cool, but is there an easy way to hook it up with Kafka? And there is. There's a library called Reactive Kafka that does this. It's an Akka Streams wrapper around the Kafka API. It was originally written by a company called Software Mill, but it's now a top-level Akka project. So it provides a Kafka consumer source and a Kafka producer sink. This might seem kind of backwards, having a consumer be a source and a producer be a sink, but it makes sense. So the consumer is pulling messages from Kafka and then emitting them into the stream. And the sink producer is receiving messages from the stream and then producing them into Kafka. So the producer is a sink that can send messages to Kafka topics. It can also be a flow that sort of produces the message and then emits something downstream that says, I just sent this message. And this is useful for, say, logging when a message gets produced. The Kafka connections are automatically managed. So when the sink is connected, the connection will be made. And when the stream completes, it'll be disconnected from Kafka, which is pretty nice. Similarly, the consumer is a source that pulls messages from one or more Kafka topics and then emits them downstream. It's able to auto-commit messages, providing at most once consumption, or you can pass an offset object downstream that you can later use to commit that offset to Kafka, giving you an at least once consumption semantic. So if it crashed in the middle, you could just start it back up and it would get duplicate messages from before, but you could deal with that in your code. So if it receives back pressure from downstream, it simply stops asking Kafka for new messages, which is really nice. It sort of works really nice with Kafka's pull model. And when it's materialized, you get this control object back that you can use to stop the consumer and complete the stream. And like the producer, the Kafka resources are managed automatically. When the stream starts, it connects to Kafka. When it stops, it just stops consuming. So some example code. Hopefully this is readable on the projector. You need a few things. You need an actor system. You need an actor materializer, which is what Akka Streams uses to actually create all the actors and do stuff when it materializes and actually runs the stream. Then we just have to set up some producer settings, which say which actor system to use, what serializer you're going to use for the message keys, and what you're going to use for the values. So here we're using byte array keys and string values. Then I'm creating a source that just emits the numbers 1 to 100, changes it into a string message, creates a producer record, which is what Reactive Kafka uses to send the message to Kafka. And here it's sending it to a topic called lower. This then gets sent to a producer sink, which actually when you run it, will send those messages to Kafka. So it'll send 100 messages and then stop the connection to Kafka. Pretty simple. Similarly, the consumer, you need an actor system and a materializer. The consumer settings look really similar to the producer settings. You just say what type of key and value, tell it which Kafka server you are, and then you also specify the consumer group ID, which here is test group. And here we're creating an at most once source, which will auto-commit the offsets to Kafka when it receives the messages, telling it the topic we're listening to, which is lower. We're getting the value, and then we're sending it to a sink that just prints the messages out to standard out. And then later on, we can call this stop method on the control object, which stops the connection to Kafka and completes the stream. You can also combine the two. I've omitted some of the boilerplate. But here we're using a committable source, which also passes an offset object down through the stream with the message, which you can use to commit the offset. Then we're creating a producer message. This time it's a little different because we need to pass along that offset information. And finally, it's sent to a sink that knows how to commit the commit the message back to Kafka. And so here, in just a few lines of code, we have at least once delivery. The offset's only committed after the message has been processed and emitted to the downstream. We have full back pressure. For example, if it's being slow to produce messages, the consumer will just stop asking for more messages, and nothing will crash. And it's pretty easy to read. We did a bunch of transformation here in just a couple lines of code. It's a super simple example, but it just shows how easy it is to interact with Kafka this way. So I'm going to show you a quick demo, hopefully it works, of how easy it is to use. Okay, so I'm going to use Ammonite REPL, which is a nicer REPL than the Scala REPL. Let's see if I have my, oops. So I have Kafka running on my laptop. I also have two console consumers running, so I have two topics. I have a topic called lower and a topic called upper. I'm running the command line consumer, so on the one on the left is the lowercase, the one on the right is the uppercase. And then I'm going to show that case of taking in lowercase strings and uppercasing them. So first of all, I need to import some libraries. So I'm going to load Akka Streams, and then Reactive Kafka. I have them cached on my laptop, so it should be quick. Then I need to import a bunch of imports, so it's the Akka, Kafka, Reactive Kafka, all these imports. Then I'm going to create the actor system and the materializer. So that's running now. I'm going to create producer settings that say to connect to the Kafka instance that's running on my laptop. And say that I'm using string values. Then I'm going to create a consumer that's going to consume from the local Kafka instance as well. And I'm giving it the consumer group ID service1. Now I'm going to create the actual consumer and run it. So you can see here, it's basically the example verbatim from that slide. So now I have this control object that I can later use to stop the stream. And finally, I'm going to run the producer. I'm using a thread.sleep here just to give me time to go to the other window before it emits the messages. So we should see the messages being produced on one side and then the actual result of the stream running on the other side. And so we can do the same thing again, maybe give it a different message. And it'll just sit there consuming the messages. You can also, so if I stop the consumer, it's not running anymore. So if I produce messages, they're going to show up on the left-hand side, but they're not going to be on the right-hand side. But then if I start up the producer again, or the consumer again, so it's running, the messages will be consumed, hopefully. There's a bug in this version of Reactive Kafka, so if I run it again, it's going to work. I don't know why, but the Reactive Kafka is still in a milestone for this version. I don't think it's completely ready. But it picked up where it left off and consumed the rest of the messages. So to wrap up, microservices have a lot of clear advantages, but there are trade-offs you have to make with increasing chances of failure and complexity. Asynchronous messaging can help with that, and Kafka is a great system for doing that. And finally, Akka Streams and Reactive Kafka can make it easy to reliably process data from Kafka in your Scala application. This is what an architecture might look. You have Kafka in the middle, and all these services talking asynchronously, sending messages using Akka Streams. Thanks, that's it.